My name is Rick Kleinau. I'm a sales engineer at Fluke. I'm going to use a very simple waveform, DC voltage from a 9-volt battery, to show you how to read the settings on the scope meter. Now, the purpose is not for you to learn how to control the scope, but simply to learn to read waveforms. To really appreciate measurements on a VFD, you need to understand waveforms. So I'll use the battery also to give you a sneak preview on a more complex waveform called pulse width modulation. My test leads are connected to channel A on the scope meter here. I'm using this dual banana plug so I can make an easy connection to the battery. Now right now, if you look at the scope, my test leads are open, so the scope's just displaying noise. Okay? In the upper right-hand corner of the screen, it's telling us the scope's in the automatic mode. Now, this is a feature that we call connect and view. What this does is allow us to simply make a connection to a test point. The scope then will control the settings so that I can view a stable waveform on the screen. This is happening in real time, so I can go from test point to test point. Remember too that this is a digital scope, so it's continually making measurements, a process called sampling. The numbers, the samples, are recorded into memory and used to draw a graph, and the graph is the waveform. It's a simple process. It just happens very quickly. This particular instrument can sample at 5 megasamples per second. That's 5 billion readings every second. We don't have time to discuss it in detail, but the trigger function in the scope, the trigger setting, determines when it's time to take the numbers from memory and just draw the graph on the screen. And when it draws a graph, it does just what you'd do if I gave you a list of numbers and asked you to plot them. You take the first number from memory, put a point on the screen, the second number, and just draw a straight line between them. Okay? If the actual waveform being measured is repeatable, then the trigger setting will cause each new graph to fall on top of the previous one. If you look closely now at the screen, I've actually connected the battery. You can see that it's moving a little bit, so that graph is being continuously redrawn, one on top of the other. So now we have a stable display, and it should match the pictures in the PowerPoint slide at this point. Now the area at the top of the screen here, you see meter readings, voltage on the left, frequency or hertz on the right. The capital A here, well, in both cases, tells me that this measurement is being made on channel A. The color red also tells me that it's channel A. Now, one thing you might not have seen before, if you look at the voltage reading here, there's the V for volts with both a little squiggly signal that represents AC volts, but also a flat line for DC volts. What the scope's doing is adding the RMS value of AC to the DC voltage. Now, most meters can't display AC plus DC. It's one or the other. But most scopes can display both AC and DC, either one or the other or both. You know, one example of where it's important to be able to isolate the AC, the DC component, or put them both, is when you look at the DC voltage on a variable frequency drive. Right? Well, it's easy to know what the meter's doing by looking at the readings at the top, right? The frequency is 0 because the battery has no AC in it, so we expect that. But you can also determine the battery voltage by looking at the waveform if you know how to read the settings. If you look at the screen, you see the divisions, both vertical and horizontal direction. The x-axis here is the time axis, and in this case, the y-axis represents voltage. The value in the lower left-hand side is the scaling for the voltage axis. So we're set up right now at channel A is set to 5 volts per division. So it's 5 volts between each division. The capital A tells me that's channel A. The color red tells me it's channel A also. to actually determine the voltage level, given that I know the spacing between divisions, though I have to know where 0 is. This capital A, the red color, tells me that for channel A, where the rectangle's positioned, this is 0 on the graph. So to read the voltage level, I start at 0, 5 volts, 10 volts. It looks like a 10-volt battery if I just look there. Now, a DC waveform isn't very interesting because it doesn't change in time. So I really don't need to know anything about the time-based setting because nothing changes. But if you look in the lower right-hand side of the screen here, this is the setting for the time scale, 10 milliseconds. MS is milliseconds per division. The little icon in the middle of the screen, it looks like a musical note, is called the trigger icon. This designates time 0 on the screen. Everything to the left of the trigger point is the graph for readings that were taken before the trigger conditions were satisfied. Everything to the right of the trigger icon, or the time 0, these are samples that were taken after trigger conditions were satisfied or after the trigger point. This is, we just don't have time to talk about triggering, but the ability to position the trigger point in time is one of the most powerful features really on the digital scope. Well, I'm going to switch polarity, and just by flipping the battery here, and now you see we get a negative waveform. That is, here's 0, still at 5 volts per division, -5, -10. It looks like a -10 volts. If you look at the voltage reading, the reading on the top, you don't see a minus sign. That's because we're doing the AC plus DC coupling. And the RMS values on the AC don't have polarity. Well, now you're an expert on reading the settings on the scope. I want to give you a little view on how a pulse width modulated signal is created. I'm going to change the time base a bit. We're set at 10 milliseconds per division now. I'm going to slow it down to 4 seconds per division. Okay. And what I'm going to do is just start by creating a few negative going pulses by just lifting the leads off the battery. Then I'm going to switch polarity and make a few positive pulses. Now notice when I make a pulse, I can't change the amplitude. That's fixed. It's going to be the battery voltage. I can choose polarity, positive or negative, but not amplitude. The thing I can change is the time base, or well, the timing. I can determine how close together pulses are, and I can determine how wide they are. Let me stick a few more negative pulses in here. Then I'm just going to stop it, hold the display. What I've tried to do is simulate a waveform that's created by the inverter section on the VFD. The inverter section has as its only input the DC bus. So all it can do is control, if it wants to make pulses, whether they're positive or negative, and it can control the spacing between pulses and the duration of pulses. So we'll come back to that later when we look at the output section of a VFD.